slide. There we go. Yeah. So what I thought I would do, maybe I'm hoping to make it weekly segments, but just still talk about a little bit about what I did for my master's research, which I normally wouldn't, I never would have thought I would have done this. But with what's been going on in the world, what I actually did research for, my advisor was into infectious disease modeling. He was into that before it was cool. So like that was his done. Now he's working with like COVID models. And if I have some spare time, I'd like to read some of them. I actually briefly went over the spring break, but some of what he's been doing recently. But I did a very relatively smaller scale research project for him, as you could sort of see there. You might, well, there's my title, you could read it there. So comparison between a stochastic and a deterministic SEIR influenza model with vaccination occurring throughout an epidemic. Maybe you don't understand every word from that sentence, but you probably understand enough that you can be like, oh yeah, this is relevant for what's going on in the world today. And yeah, I did this in partial fulfillment for my master's. The other part was more the teaching responsibility, so teaching assistantship. So it's kind of interesting, like I had sort of a crossroads when I was finished that. Do I like the teaching more? Do I like the research more? And now I'm here. So yeah, I think I always knew that. I was just kind of like nervous about teaching. And eventually I came around and realized that. But anyways, with that aside, I would just, talk a little bit about what I did and sort of in general modeling, like mathematical modeling. How does that work for trying to figure out, because I mean, it's a very hot topic issue today, trying to figure out what to do with COVID and how best to handle it. It's no easy answer. I want to sort of approach it as objectively as possible. I know there's going to be people on wide end of the spectrum, and I myself have sort of teeter-tottered in various areas, and I don't think there's an easy answer. But anyways, I'll start with the very basics. I'm going to start just like with you guys. You're going to be doing a research project, or you already started. And like one of the first places you want to start is, especially for some of you, I mentioned this in your feedback, read the feedback, but it's like if you're doing something that requires background info, like maybe you have something that there has been a lot of research in the past, you want to read through that. You want to read through what's been done before. You want to sort of motivate the significance of it. You want to define key terms so that people know what you're talking about in the presentation particularly, but also in the write-up. So that's what I'm going to do. I'm just going to model that for you. So I think I have 4 definitions, and then I'll talk a little bit about a very basic model, like the basic bare bones model. By no means is it supposed to be any sort of revelatory thing, but at least to sort of get your idea of what mathematical modeling entails. So first definition, I don't know if people are familiar with this one. I think some of these terms I've talked about are now mainstream because of COVID. Reproductive number, sometimes it's called R0. So basically all that is it's the expected number of people that the first person will infect, sometimes called patient zero, the first person in a community or a country or whatever. It's how many you would expect them to infect. And that little diagram on the right, sort of in probably what you'll notice, or you recognize, oh, that's exponential growth. We talked about exponential growth in grade 9 as well as grade 11 with geometric series. And at the beginning of an epidemic, exponential growth is a good way to model it. However, what about when so many people are, for example, if there's been no social distancing, or maybe nothing has been done, at some point, so many people are going to be infected that like the exponential part will sort of tip off, because then like the 2 people that the next person infects, maybe they already have it. So, and also like if luck or hopefully we get a vaccine out, what we do now, but like before we didn't know that when that would happen. So vaccine, and another way is like social distancing. That will also, like once the disease comes in, like, so R0, the key thing there being 0, like at the very beginning. But as the disease progresses, that number is going to sort of change. It'll probably get lower. Like for example, with COVID, it probably started a little over 2, if I remember the research correctly. But then as people socially distanced, as people wore masks, all these different strategies that people, at least I would hope the research has been into, that it actually lowers the reproductive number. It makes sense that it lowers the reproductive number. And we've been doing all these things in the hopes of getting that as low as possible. The other way is a vaccine, which we now have as well, that is helping as well. But one important insight from this reproductive number is whether or not it's bigger than 1 or less than 1. That's absolutely critical, because if you remember from exponential, some of you might know from exponential, if you have a base that's bigger than 1, you get growth. If you get a base that's less than 1, you get you get decay. You want decay because infections are bad. So if you have a number that's like really close to 1, let's say 1.1, 1.2, you'll probably still have a growth, but it might be small enough that your hospitals can deal with it, right? So there's difference to, it's not an easy question still, because some of the distancing measures that we do, or some of the interventions that we do have a high economic cost. They have a high mental health cost. They have other things. So it's not an easy question to all these, to mathematical modeling. And I think the best models sort of incorporate both sides of the argument and try and simulate that. Another definition, herd immunity. You guys might have heard herd immunity. Basically what that means is if you don't actually have to vaccinate the entire population in order for the outbreak to close. I'll explain that in a little more detail. But basically enough people, either by a vaccine or by getting the disease and recovering, once enough of that happens, then the outbreak sort of stops. A simple example would be, let's say the reproductive number was 2, but then we vaccinated half the people. Well, if that's the case, then let's say patient 0 comes along, they infect 2 people, but one's already vaccinated, so then they don't get to infect any more people. That's just great. So now the reproductive number is essentially 1, which means there's probably not going to be an outbreak. The higher R0 is, the more higher percentage you need to reach herd immunity. Yeah, that's the general idea, and diseases vary depending on R0, and not only that, but like it matters where you live. Like if you're in Toronto, where you're going to be contacting people more, it's going to be a higher reproductive number than, let's say, you're in Wallaceburg, where I am, or Chatham, even less dense. So there's a lot of variables, and models try and figure out like what are the most important variables, and can I include them in my model in a way that's feasible? One common way is what I have definition 3 net here, SIR models. S, susceptible. You haven't gotten the disease yet, but you could potentially get it. I, infected. You got the disease. Straightforward, explanatory. And R, recovered. And some models include an exposed, and that's basically saying there's a period between when you don't have the disease and you are infected. There's sort of an exposed, so you're exposed to the disease. You're not showing symptoms yet. Some models include that compartment as well. So a compartmental model is any model in which you basically have a certain number of people in each category. So that would be what we're doing when we're trying to model. When we're trying to model an infectious disease, basically, you probably start with most of your population in S, and some people in I. So like basically a few people get infected at the beginning, and then we see what happens. We press play and see what happens in our simulations. We'll talk about simulations in a moment. And if you're lucky enough to have a vaccine before the epidemic starts, then you probably have some people in R because they're vaccinated. Now the tricky part is like the transmission rates and like the recovery rates. These are all parameters that you have to sort of collaborate with the scientists and figure out exactly, or maybe what are some plausible values for that. So you make some models always have assumptions in them, and you really have to, sometimes we have to sort of test assumptions. I'll talk about that in a moment, but yeah, I just want to get you a feel for like, when people say, oh, trust the mathematicians and the scientists, there's a lot, it's more complex than you think. And it's like, there's a lot of different opinions on it, even within, the scientific community on what's the best course of action. Anyways, with that aside, I'll finish with my last definition, which is time series. Time series we've actually dealt with before. All of you took grade 11 with me, we did amortization tables. So we did the whole activity where I had you basically have 4 categories: principal, interest, remaining balance, and then I guess it was your month number was the other one. You had an equation that you put into your Excel spreadsheet, and then you copied that and you pasted it down for a whole bunch of time steps. You could actually do a very, very similar process to help model an infectious disease. And I'm actually going to show you, I did a very quick one over the weekend just to show you how easy it is and to do like a very, very basic model. Now, the one I did for my master's research was a lot more advanced, but you can do a basic one very, very simply. So I'll have some fun with that at the very end of this little section. Basically, I wanted to also, because this is sort of getting into my research I did, is I compared two of the more prominent models for modeling an epidemic. So one of them being deterministic model, the other one being stochastic model. I would summarize it this way: deterministic, you're using calculus basically. Stochastic, you're using statistics and probability. There's advantages and disadvantages to both. You see the calculus likes smooth curves. Not surprisingly, that black curve is the deterministic model for some hypothetical town that got infected with a disease, starting with like a few people and then pressing play. So the strength of the black curve is, well, it's relatively easy to implement. I'm actually going to show you, as I mentioned. It's pretty surprisingly accurate if you have large populations. Weakness, well, if you have small populations, you're going to have silly predictions like, oh, we can expect like half a person to be infected. Well, half a person? That's not possible. So it's kind of like deterministic, and like you have that smooth curve and you get things that aren't perfect, but they do a pretty rough estimate of what you might expect in most cases, not always. Stochastic models have strengths in which they use basically some of the stuff that we've learned in this course. Like binomial distribution would be one example, but use probability techniques that we've learned about to simulate what might happen. So now it's no longer possible, like for say half person to be infected, but let's say each time step there's like a probability that the first person will infect another person, or maybe there's a probability that they'll recover, and you can set that up using a simulation. That's just a lot more helpful, because basically you can see what I have there. I ran multiple simulations, and you can sort of see, even though the black curve predicts one thing, if you actually press play with sort of accounting for randomness, you can see the wide range of possibilities, and then you can sort of plan accordingly. So the weaknesses would be that it's a lot more complex, which means more computing power. You have to balance what you think is most important in your model and factor that in. And you can't, there's no way you can simulate real life like completely. That you sort of have to pick the ones you think, and you have to use intuition. There's a lot goes into it. Want to talk a little bit about simulating and why we would do that. So you guys will be doing a research project where you'll probably be collecting data. So you'll take a sample, or maybe some of you might be experimenting. I don't think anybody, but you could do that. That was an option as well. Or you're observing data. Simulating, the problem is for an epidemic, it's not like you can try something and then rewind time and then try it again. So unfortunately, you can't. You only get one shot at it. So sort of the next best thing is to try and simulate what happens in the real world, and then press play on your simulation and then see what happens. You can sort of record some things like infection, how many people got infected in total, but probably more relevant would be like, what's the maximum caseload? So like, we want to flatten the curve. We all know that saying. Would be like, okay, people are going to get infected, but let's try and make the curve wider so that we don't overburden the hospital. Hospitalizations and deaths could be other things you want to make sure that you minimize. But I think the good models also look at the disadvantages to intervention strategies. So they sort of do a cost-benefit analysis and say, okay, what happens if we close the schools? Okay, we can expect the hospitalizations and deaths to go down, but what about maybe deaths from suicide or deaths from people that had to, we're going to get another type of surgery and had that delayed. So there's not an easy answer, is what I'm saying. And if you're looking at researching models that have been done, I would suggest looking at ones that took a thorough approach at it, rather than just say, oh, we got to get infections to zero, because I think that's oversimplified. So you have to sort of, it's not an easy. I'll just say that. So simulations, basically you start with a research question, just like you guys. We'll start with a research question. You try and implement the research question in your simulations, and then see if you can answer the question with your simulations. That's sort of the idea. And then hopefully the simulations give you some insight that might answer your research question, and then you can, try and see what the best course of action might be. There's a probability component, as I mentioned, to simulations. For the stochastic case. The deterministic case, there is not. So the simulation that I did in my master's took that into account, took the randomness into account, and actually compared it for the models that did not take randomness into account. Another thing I should mention is that there's certain things, let's say reproductive number, I talked about that. Well, maybe there's some guesswork as to like, is it 1.5, is it 1.8, is it 2.1? Well, with simulations, you could, even with deterministic, which I'll show you, but especially with stochastic, you can like run a few different simulations with the different R values that you think are plausible, and then see how sensitivity analysis is basically, well, how, if I change one input, how much will it change the output, total infections or total deaths, or whatever you think your output variable should be. So we have things like infection rate, vaccine efficacy. These are all things that you have to really research to make sure you get them correct. If you're not totally sure, you can try a few different values that you think are plausible. And you can even do binary things like whether or not you close the schools, or whether or not people are wearing masks, or maybe as a percentage of what people are wearing masks. And you'd have to do a lot of research. Okay, how much do masks actually help? Because that's not even an easy question to answer. So you can see it gets very complex, but we're going to start very, very simple. So mathematicians, we start with the simple model, and then we add things that we think are important, and we see what happens. And so the basic bare bones model for infectious diseases is called SIR, or SIEIR, or even simpler is SIR. So this is what I'm going to end with, at least for this part of the segment. I hope to do more on this, but I'll just show you how easy it is. Well, basically, you might remember for the amortization project in grade 11 that you had like inputs, you had your loan and you had your interest rate. Well, for SIR models, the same sort of thing. You'll have a population. Chatham's about 100,000. You'll have a certain amount of people that come in with, let's say they got COVID, and then reproductive number, which could be around 2. It's probably less than that, especially now that the schools are closed and that we're doing all these measures. But let's say if we didn't do any of those things, probably 2 is pretty reasonable, I think. But we'll play. Nice thing is we can play around with these inputs and see how that changes the output. So that's what I did. You can see basically I put an equation for infected that basically said, okay, some of the people, because there's 2 people infected, they're going to sort of be a burden on the susceptible. Some of those susceptible people are going to get affected by the infectious people, but some of those infected people are going to recover. And so you're going to have that sort of pattern going on. So I accounted for the people that would recover as well with a subtraction sign. And then I put formulas in for all 3, just like you did for your amortization table. And you just had to scroll down, and then you could make a graph. So the blue line is susceptible, yellow line. Actually, when the yellow line flattens, you've reached herd immunity. And the red line is you're infected. I actually made a graph right below just for infected. So you could see in this case, this would be kind of a worst case scenario. It also, I should clarify, it also means that like this model assumes that we're just walking around randomly without any aim or purpose. We're not in reality, that's not the case. Like you're not equally likely to infect some random stranger than you are to infect someone in your own family. You're much more likely to infect someone in your family than this model doesn't account for that. It's a very simple model. It just sort of imagines us as dots going through space, and so if you accounted for that, you'd probably decrease the expectation. But this is like a crude, I would say it's a very crude overestimate of like worst case scenario. And so you could see like, okay, at one point there's like 15,000 people infected. So I don't think we would have even close to that. But again, we've done a lot of intervention, like the government stepped in and said, you have to do this, you have to do that. So let's see, people are mostly compliant, and let's say you do 1.4. 1.4, it will change that and see what happens. So R0, you can see, look at that, way lower. So we have flattened the curve, right? And social distancing in this simulation worked decently. Still have a decent amount of people at the peak of it that are infected, but we flattened it significantly, comparatively speaking. What if you had changed your population, or no, your initial infected to like 10 instead of 2? So maybe it was like a group of people. Well, it actually doesn't change it that much. So it's the reproductive number that is the most sensitive to changes, as we can see. So I don't know, it may change it a little bit, but not much. So like reproductive number, getting that low is like absolutely crucial. And that's why a lot of policy. So I can sort of respect that sort of thinking among, it's the rationale behind a lot of what's the decisions that are being made. There are arguments to be made on both sides, but at least you could sort of see that side of it. So yeah, you could play around with this. You could change the population size, let's say Wallsburg, and then you could see what happens then. So it's nice. You can kind of do an experiment, even with the deterministic case. Now, what I did was simulations using probability. You can't do that on spreadsheets. You have to use another statistical program language for that. Maybe I'll do that. I'll show that in another day. But you can do deterministic model very quick. So yeah, I think that's the first part of today, and then I'm going to introduce sort of the next part of the course. But I want to stop recording for the case of maybe there's some people that in other classes that would find this interesting as well.